Now, the two quick recap. So, what? Quick recap. Just these quantum dots depends on the band gap and size of the nanocrystals. And when size increases, band gap decreases. So you have different wavelength of light. Depends on the band gap. You can get invisible window emissions, or you can get from NIR, mid-IR. Depends on different nanocrystals, and you can see that here the valence band is made by the anions, and conduction band is made by the cations. So, and you can get tunable emissions, as I told, from whole visible window from 400 to the 700. It's based on cadmium selenides. But if you go to the other, like lead sulfide, lead selenides, and mixture of the different cadmium sulfide selenides, and there is plenty of different of nanocrystals. So you can get different light emissions, and these are far more better than the dye, because already these things I told. But just to recap, because now I am going to tell about the application kind related things, and these are more about mostly much more better than dye, because of these are very tiny and super stable in air, because it's a nanocrystals. It's a crystalline form, and it's not degraded. Yes, it degrades, but depends on the different kind of nanocrystals. But generally, cadmium selenides and copper zinc sulfides and other things, these are not degraded. Now, you people will tell that, and you see that these are very bright. Now, many people tell, okay, cadmium is a very toxic. Yeah, that's true. Cadmium is a toxic. So we have a solution to remove the toxicity. So generally, people give the coating with the zinc sulfides, so there will be no cadmium leakage for the applications. And when you put the zinc sulfides, it is much more stable, in much more stable. So now the come to now I am going to my next presentation. So it's a kind of different kind of application of the quantum dots. There is two different part of applications. One is biological applications, but as I am not too much interested in biology, so I am not going to tell anything about the biology. But there is another kind of applications, like a different optoelectronics applications. For example, here light emitting diodes, solar cells, field effect transistor, and it's a phototransistor. So this kind of applications is very nowadays very common for the quantum dots. And now the question is, because it's a nanocrystals, but the question is, how can we make a good film of nanocrystals? And we need to, as I told you earlier, these crystals are fully covered with a long chain ligand, and these are completely non-conductive. So you need to remove the ligand from the surface. Otherwise, your device is not a you cannot compare with the device with the other established devices. So things are, so now, how we generally nowadays, how the people make the nanocrystals films. So you see here, these are crystals which cover with the long chains, and then it's dispersed in the solutions. You can see it's very ink, looks like ink, but when you make a film, it forms like look like this. But you see, these are really very organized. So if you don't get the organized film, you will not get good results of the electronics applications, because it's not a single crystal, it's a film, and it's a glossy kind of film. So that's why sometimes we need to do different kind of technology, especially the self-assembly. And self-assembly means, suppose there is different kind of technique of self-assembly. maybe you can dry, or you can evaporate the solvent slowly, and then you will get the nicely patterned quantum dots. Here you can see these are well organized, and you cannot see any gap, any defect in this film. And these are the glossy film, high concentrate solution when we dip cast. And these films looks like this. So it's a photo, or it's a example of one of the photo detector. So this is the basic things to make a good film. Also, you can do the spin coating, but spin coating for the making the organized nanocrystals, spin coating is not a good idea. But if you make a very thick film, then spin coating is okay. But if you make a thin film and monolayer or bilayer based, then self assembly is the best way to do. So there is many different procedures to do self assembly of the nanocrystals, mainly quantum dots. Like here in the left side you can see solvent evaporation. So you choose a quite a high boiling solvent, not a hexane, means boiling point should be the above 100 degrees centigrade. So above the water, boiling point of water, because in air we have a moisture. So we need to the high boiling solvent and water. So solvent can remove slowly. Otherwise, because in air there's lots of moisture, so due to the saturation of the moisture, the solvent can go fast. Like if you took a toluene or hexane, it can go fast. So you need to add very like a octane, decane, so it can remove slowly, and the nanocrystals slowly aggregated, and when it's aggregated on the film, it's organized on the surface. So similarly, if you can evaporate it from the tilted vial, because when vial tilted, the concentration is higher in the corner, so it's again organized due to the force of attraction, van der Waals force of attraction. Another one that you can see, sorry, the over the polar liquid Teflon, like these are suppose a Teflon, and the blue part is a polar liquid, like a high boiling polar liquid, like a ethylene glycol, diethylene glycol, and then you can drop a certain concentrate of the solution. So when a solution evaporates, so it float on the surface of the polar solvent, like a ethylene glycol, and just you can collect the film. It's kind of 1 or 2 monolayer film. And also the polar liquid, so it's not a common technique, but sometimes people do for using the technical purpose. And also the gravitational sedimentation, but this is not a good things to do for the self assembly, because it assemble very way, but it's form a supercrystal. So when it's form a supercrystal, you cannot use as a put film. So it's a crystal. You can use it other purpose, like a lasing, like a for example, like a lasing, and for superfluorescence, this kind of things. Similarly, again solvent distillation. Generally, this kind of technique people used in inorganic chemistry to make a crystal, like a two miscible solvent is here, one and miscible, and you can add this solvent slowly, so it will not mixed immediately, but it mixed very slowly to each other. And when it's mixed, because yes, its saturation level is increases, because the solvent because these nanocrystals in the solutions, it's not it's do not like to stay in solution, so it's wanted to get down, and that time, because it's slow miscible, so it can aggregate and form a soon nice assembled structure. And also the non-solvent addition. So non-solvent vapor. So suppose you have a nanocrystals and you have a different other vapor, so it can remove. And but these two techniques is not a good for to make a film. So generally people do that this evaporated in the polar liquid in Teflon through this kind of technique. Sure. Now, for example of the film, you can see these are the gold nanocrystals. These are the gold nanocrystals, and you can see it's, for example, how it forms. You put a drop of the gold nanocrystals, and then then when you add a drop, it's slowly evaporated. And when it's slowly evaporated, initially it's stay in random way. Then when it's slowly evaporated, it's closing enough, slowly come to close together. And once it comes to close, it's getting you can say it's aggregated, but in highly dispersed form. You can see it's a form a very super monodispersed, and you can see there is no defect. And these are like these gold nanocrystals is attached through the these ghost nanocrystals is attached through the ligand here. And this ligand is forms like a interdigitated through the long chain so that's why it's dispersed very nicely. And you can see it's a nice crystalline. It forms like their distance between all the, it's very highly planed. And you can see the side view, it's very nice film. So, and the how we can see that these are form very good film or not. So first things we can see the in TM. So you drop in grid TM grid, and then you take a TM on the of the nanocrystals. And but TM is very small. You need to drop in a small place like a TM grid. So that means when you make a film, so it could not be a whole area. It's a good. So the other way to do the small angle X scattering. So it's you can take the you can see the you can put the beam on the surface of the your film, so different places of the film, and you can see the image of the reflection. It's kind of crystalline image. So from this kind of image you can get how it's dispersed on the film. And another things is, as I told earlier, you have a glycol and you put a film, and you have a cover, so it's removed slowly, and nanocrystal close together. And then you have a you have a surface in you have a substrate in the deep of the solutions, and then you can take it out and you will have a nice film. And you can see these are completely homogeneous film. And in high magnified image you can see all are well organized, and there is no crack on the film. So in this way we can have a monolayer or bilayer film. So it will be good for to make a good devices. And so as you can see here, lots of ligand on the surface. So as I told earlier, that this ligand is completely non-conducting. You have to remove this ligand in such a way that your nanocrystal will be the intact on the surface. That means it forms a monolayer film. And at the same time, at the same time, it will be also the ligand will remove from the surface. So now you can see it here. These are the ligand on the surface, like a your like oleic acids, oleamine, and etc. And at the same times, these oleic acids or oleoelement bind to different kind of way. I am not going to details about that. It's completely based on chemistry, like L type, X type. So some are strongly binded and some are not. But when you need to exchange on that, so you will have some kind of different polymers or other ligand which can remove this long organic carbon, and these are also removed by slight heating. So there is two way to ligand exchange. One is you exchange earlier, like here from solution to the upper, and then from here you exchange the ligand. So after ligand exchange, it comes to the other solvent and then deposit. And deposit is a film. And another thing is you first deposit and then exchange with the ligand. But as different literature point of view and as my experience, tell that this process, like if you deposit first and then remove the ligand, is a good process to connect the dots. Because if you don't connect the dots, your film will not be good enough to check to get to move the electrons or holes on the through the film. Like here, you first exchange in the solution, and when it's exchanged in the solution, so these are not oil dispersed like earlier. So it's oil dispersed for certain time, like 1 day or 2 days, but after that it's trying to get aggregated, because you do not have the van der Waals force of interaction in the solvent. So it's tried to stabilize themselves and it gets precipitated. That's why you can see the film as is not quite nice. It's a random aggregated kind of film. But here you can see you deposit first, and when you deposit, it's homogeneously dispersed on the film, and then you exchange the ligand. So when you exchange the ligand, it's come close enough because it's already, they knows their positions on the surface. So when they knows their positions, you remove the ligand and it close together, and when it's close together, you can see these are so close, so electron can goes from one to another. One to another. So, and these ligand goes through the electron hole goes through the hopping. So last talk, someone asked me the questions how the charge goes through this. So these are goes through hopping. This hopping means it's, if you put a bias, so it generates an electron or hole, depends on your nanocrystal's property. So electron goes from here to there, there to there, and this kind of hopping techniques. Next, it's called next neighbors hopping model. So, and if you have some defects, so when it goes through one line or another line, if you have a defect inside the film or inside the monolayer base, so it cannot go, and you have a loss of this electron. So that's why you, for the better efficiency device, you need to have a very high quality of the film. So now we know that how to make a film, and we can do the spin coating for the photovoltaics. Yes, spin coating is the best way to do, because in that way you no need to make a completely one monolayer or two monolayer. You need a thick film. So for that, it's aggregated structure also fine. So you just need to remove the ligand. You need to remove the ligand. So now, you see in all my talk, it's a fluorescence based material. These are super fluorescence, and sometimes the quantum yield is very, very high. So people first use the spectroscopy related applications, and then they are interested about the light emitting diodes. So how the light emitting diodes works. So here you can see these are the very basic structure of the diodes. So you have a ion conducting surface where you can use the ITO, indium tin oxides, and then you have a p-type layer. It's a polymer, p.pss, and then here they use another layer, generally people don't use this. So you have a quantum dots on the surface on the film, and then you have a n-type layer. It could be TiO2, it could be zinc oxide, it could be other polymer film, and then another contact of aluminum. So when you give a voltage, so the electron hole recombines through this. When it recombines, it emits lights. So that light pass through this ITO sites. So how this way it works, and you can see it's a band structure of these films. And when you keep the bias, so you can see hole is moving through this, and hole is comes to the valence band, and the electron is comes to the these contacts, and when it's recombines, you will see the emission of the light. Now the things is how good the emission is. So depends on the different band gap and band structure, band engineering, you will get the different yield quantum yields of the from this quantum dot based LED. And these are the region nowadays. These are so famous already. Samsung made the quantum dot LED LED TV. So how it works? You know that in LED TV, general LCD TV or LED TV, we need to have some light absorbance material which can absorb scattering light. So, but for quantum dot LED TV, you do not need the absorbance materials, because we have a different size of nanocrystals which can emit only the different wavelength of light, like blue, green, red, yellow, orange, different. When it's depends on size. So generally it's a backlight, and black light has a blue LED, and then you have a quantum dot layer, and it's a kind of monolayer type of themes. And then when blue LED is shining the light, so it's emits. So, and it's reflects on the it's reflects on the screen, so you can see the highly bright and highly color purified image. And it's a very basic phenomena. And you can see here is you can see backlights, and it's a quantum dot enhanced film, and we have a panel, and we have a color filter glass, so it filtering the lights, and we will have a very bright white light emissions. And as I told, these are different size of nanocrystals. So you will have a different layer of the to make a you do not people do not make mixture of the nanocrystals. So we make they make the blue emitting nanocrystals, like a 2 nanometer nanocrystal one film, then green, then orange, and then red. So you will have a very bright white light emissions, and then we can see it in screen. So now you can see as these nanocrystals are highly dispersed in the solution. So people wants us to use make it in the film in a flexible kind of thing. So when it's in flexible, so you can when it's in flexible, you can use it in your clothes, in your skin, in different of surface, because surface. So you no need to keep it will save your space. It will save your space. So you can see these are the different examples. So here some devices you can make a heart rate, some devices, so you can have a touch sensor, you can see the eye vision and screen, and you can also so flexible, you can flex it in the surface of your hand, and you can see the different kind of devices uses on your hand. It's no need to space so much. So, and these are one example of the flexibility. As I told, you can see there is lots of nanocrystals. Is very bright and size of the nanocrystals, and you can see the wavelength. We can get different emitting wavelengths from the different nanocrystal. These are the cadmium selenites. So it can tune from the 400 to 700. These are cadmium tellurides. It can tune to 600 to 900. These are the lead sulfide or lead selenites, so it can go up to 800 to 1,400 IR, so you can have a IR detector from these quantum dots. So it will based off the night vision camera, night vision technology. And another quantum dots is a 3,5 like indium phosphides. It falls in the visible region. And lead telluride, it's a very good material, and generally it's a p-type material, but it's little bit hard to synthesis because of the tellurium. And another is the Indian arsenides. It goes to very broad region from the visible to the NIR. So, but as you see, as you can see, all are quite a bit of toxic except the copper-indium sulfide or copper-indium selenides. The problem of this ternary compounds is it has a very defect states in the crystal, so the reproducibility of the quantum field is very less. So and so these are the things people mostly use in the different kind of electronics. And you can see here these are the different wavelengths, is NIR wavelengths of NIR emissions, and it's covered with the ligand. And when we make a good film or good quantum dots LED type of devices, you can see uh, it's a color coordinate, and here is the sunlight where we can see it's 100%. And generally HDTV standard color triangle, which belongs to this, so a very small region. But when you have a quantum dot color gmod, so it covers almost whole coordinate. That means that tells you that it is a better opportunity to make a LED kind of applications, mainly specifically for the like a quantum dot TV. It's quite a bit costly, but if you say the efficiency purpose of things, it's a bit longer efficiency, because in the normal LED TV, LED TV or OLED TV, OMOLED TV, we the company use the different kind of dye or polymer on the surface, but at a certain point of view, it's getting degraded and your resolution is getting decreases from 4 5 years. But the quantum dots, it is basically coated with the silica, so it's get it super stable. And it's they checked, it's more than 10 years also, it does not get any did not get any lose of the resolutions of the images. And these are the how they make they don't use the pure quantum dots. They use the zinc sulfide or zinc selenide cells, so it can have a much more stable. And you can see how bright it is. It shows also in device, and it's a green emissions. It's a green emitted because of the brightness in the camera could not take the pure green. It looks like white, but it's a green. And you can see um, the EL intensity and the peak and the spectra of the EL electroluminescence. It's a very nice and very nice shape. And here also, if you put the different voltage, and you can see its brightness increases, and it's a pure color emissions. So this is another example to improve the color display. So it's a patterning technology, so you can use a different pattern in the surface of the quantum dots. Like you have anode, whole transport layer, quantum dots, and electron transport layer, then cathode. Okay, so you can change the whole transport and electron transport layer according to you whatever you need. For example, here the devices works like this. Hole moves through the whole transport layer and comes to the valence band, and here the electron moves this electron transport layer and moves to the conduction band, and it's recombines, and you will see the different wavelength of the emissions. So now for the making device, you can use, or like here, you can use the whole transport layer and electron transport layer organic material. And so it's a inorganic organic type of things, and some are uh, only one organic, so you don't use the electron transport layer. Just you use such a cathode, so it can transfer electron to the quantum dots. And here you can use the all inorganic, means your whole transport layer also inorganic, electron transport layer also inorganic material, means different nanocrystals, like electron transport layer is zinc oxide, and whole transport layer is some other inorganic materials like a tin based materials or different way. So, and also the you can mixture of the different organic and inorganic. And here these are the peak of the, you see is that when time increases from 1990, it's past quantum dot, it's happens in 1994. And you can see when time increases, the intensity of peak intensity means your intensity of the LED display is getting higher and higher. And the highest till now is the hybrid. Hybrid means you will have a mixture of inorganic and organics. And here also another in the maximum brightness, we have see the maximum brightness in the also the hybrid structure. Is the green point, you can see the hybrid structure of the hybrid, means one surface is the organic and one electron transport layer is organic and one electron transport layer is whole. So and and how they make the basically make the flexible white quantum reality. First, here you can see uh, the spin coating and press technique. So here you can see first we spin coat the quantum dots on the surface. Then we need to make some structure. So structure. So when we make a structure, this is a template. So you put on the surface, so it attaches to the these places, and then take it out and print in the another substrate. In that way, you will have a different patterning of the quantum dots. And these are the one example how you can see the this is a lab made display, and you can see very nice butterfly in the display of the images. And so this is a technique, and then they adopted different company, and so they can make a more brighter, because this is a lab made, but when it goes to industrial level, they have a robotic arm, so you can higher control over your making film. And these are the another example how to attach a film and it get a white light. So how you get a white light, you can see, it here. Either you will have a mixture of the quantum dots in the one layer, or you will have a different layer, blue, cyan, green, yellow, red, this one by one. And it's a and when you put the bias, so you will have a each end emission, and when it comes out, white. So in my opinion, these are the best way to get a very good white light emissions. Like you see here, these quantum dots, when you mixed the hopping, as I told, it's passed through the hopping technology. And because of the bigger size, red or bigger size, blue or smaller size, it cannot make a good film. So bigger is taking much more space, and smaller is taking small space. So it will be the random, like a one room, you have a 60-year-old person and also 2-year-old kid. So it will be, they cannot be organized very well. But here, if you organized the film like a small particle or small quantum dots in past, then little bit bigger, and at the end you have a red higher size, bigger size quantum dots. So you will have a nice film, and you can make it. Here you can see these are the basic structure of the different film, red, blue, then again green, again blue. So you will have a different, and you will get a nice white light emissions from the this kind of devices. Now these are mostly on the LED based on application. There is lots of work on the LED. I just gave you some example and some best example and some of the real applications. And if you go to the supermarket and shopping mall, you will have you can see the very bright QD in the Samsung store or different big store. So these are the real applications. Already it's done a few years ago, and it's now it's quite famous in some of the Europe and also the US, and I do not have any idea of the India, but these are quantum dot TP is quite famous in US. So now another application is solar cell. As you may know from some of the other colleagues talk how the solar cell works and other things, so basic things. So I am not going to details on that. Generally, we use the it's a quantum dot solar cell. It's the basic fundamental is the same like others, like dye sensitized or silicon, but here things are a little bit different. Like generally people used the nanoporous TiO2 or the N-type layer, and then quantum dot films, and you will have some P-type layer. People use the spiro, some polymers, or you can use the also inorganic P-type material. Then when you pass the light through here, so then when it goes to light, its exciton generates from the quantum dots. So hole goes through the hole type source layer, and electron comes through the um, TI2 porous TI2 layer, and it recombines, and you will have some light. And these are the one example of the edge, as the it's from the nanocrystal solution. So you can make a flexible substrate, also the glass, and you can see flexible and glass both are gives very good efficiency, though it's not comparable with the perovskites, but these are before coming to the perovskite, these are quite famous, and also nowadays they are mixed with the perovskites and other things. And interesting thing, it can make a rainbow kind of solar cell again. You can see here, so you will have a blue, green, red kind of absorbance quantum dots. Quantum dot, it absorbs whole lights, and so it absorbs whole visible window lights, and you will have a recombination. And but these are not so much famous, so much good efficiency. It does in the research was very initial stage, and after that people get the very good material to get a solar cell applications. But these are another applications related to solar cells. These are the called luminescent solar concentrator. So you will have some glass or PMMA substrate which have embedded with the quantum dots, and you shine the lights. So quantum dots emits the emission, and it propagates through this substrate, and you will see the bright light on the surface of the film. You can see here, this is a glass. It's almost all covered with the quantum dots inside the quantum dots. So under the UV, you will see this surface is very bright. So if you put a solar cell, either silicon or perovskite or whatever, maybe put it here, so it can collect the light from here, and it can you can hide the solar cell on surface. I will give you the next idea, one example. So it is like, you can see it's very transparent, and here you can see put a solar cell, and you can have a very nice efficiency collection from the solar cell. So that's um, this is the solar illumination. So I will show you one video how it works, so you can understand that very nice way. You can see it's a
So, so, so I'm explaining here. So you can see it's coating with one film and very thin film, and you can place in the window surface on the window, so you can see through the window. It's transparent, and there is a solar. It's a silicon solar cell. So when you shine the lights pass through, and you will have a generator of the electric. And these quantum dots covered with the silica and coating, so you can have a nice film, and you can put a film on the surface and put a window. And when it's signed the quantum dots, electron hole generates, and this electron hole recombines. You will see the you will see the very bright emissions from here. And when you put on the glass or this kind of coating, so it propagates, the light propagates, the bright light propagates through the internal reflections like here. And your solar panel is in the, like, just is in the corner of the window, like here, corner of the window, and it can collect the energy, and you will have a very bright light in your room. So you no need to use the space. So you will have a space, you will have a more space, and you can use this kind of things. And this is a recent development of one of the company in US, like a UBI quantum dots, UBIQD, and they discover this kind of applications, and on the application for the solar cells. For the solar cells, it's not pure using the quantum solar cells, it's called luminescent solar concentrator. So, and now now another example, which is like a photodetector. So as you can see, these quantum dots are very bright, and bright light emissions. So it's like these kind of things, like a lead sulfides. You will have a NIR light to absorb. So it can detect the NIR light, and when it goes to the NIR light, so you will have a some IR images or thermal images, because for thermal image you need to have a NIR lights. And here also the you will have a quantum dots, and with the here they use the graphene to less down to decrease the hopping, lose of hopping of the electrons. And when you shine the lights, the electrons and holes pass to the drain and source. You will have a phototransistor kind of photodetector. So, and these are the very recent example. And as I told, these are the quantum dot display in the LED. It's a quantum dot TP. And recently they displayed, so one of the group on MIT, and they make a spectrophotometer of the quantum dots. And it's very small, and the size is look like a size is look like your mobile phone. So if you have like a mobile phone, you can use as a photodetector in the lab purpose. So it's still under research in the industrial way, but the development of this kind of things from the quantum technology is a huge achievement. So these are the most two prominent things. One is the save energy and light harvesting. Another is the light generating. So nowadays, what is this? Another materials is a perovskites. Perovskites. What the perovskite structure? It's a basically the physics people use as a calcium titanate structure. But in 1983, in 1893, it's developed it's found in a cave, and that Russian scientists, they found the structure of these things, and they gave the name of the perovskites. But nowadays, after it's developed the halide perovskite develops in the almost around 60 70 years ago, but the applications it's recently is huge. And you can see from 1893 now it's 2017 they form a crystal, they make a crystal in the lab. These are the lab based crystal, and it's these crystals is found from the nature, so it's almost looks like same, and both the structure and other things almost same. So you will have a, and these are the mostly applications as they are absorbance coefficient.
Santanu, just
Yes.
who is doing this annotation? You, someone who is doing annotation, please don't do that. Don't be a childish.
Yeah.
Santanu, can you please lock this annotation? You can go the stop and the settings are there. You just lock participant annotation.
Where it is? Yeah, annotate.
Just lock participant annotation. I will lock the students.
I do not know. I could not get it.
But the settings are security for settings would be there.
Okay.
Then maybe for your case, maybe down at the bottom.
Yeah, it's security.
Yeah, security.
Law.
Participant.
Law.
Allow participants. Don't allow participants. Annotate.
Okay.
What? Clean it.
Annotate on share content.
Yes. Just answer.
I there was a tick, but now I remove it.
Yes, you clean this.
Okay. I need to clean it.
Yeah.
Oh. Okay, done. Okay. So these are the efficiency chart of the whole photovoltaic cells in world. This is a chart made by National Renewable Energy Laboratory in US, and you can see there is these are the theoretical chart. You can get 47%, but experimentally these are up to the silicon based solar cells, and now you can see these are the, maybe I can zoom it out. This portion you can see this blue line is a silicon based solar cells, and this a red rectangle and cover with the blue is a perovskite solar cell, and these are also the perovskite, but these are tandem kind of perovskite solar cells, and perovskite made with the silicon. And it's, if I make a higher zoom out and zoom in, you can see we can have a more than 29% efficiency by using the perovskite material, and it crosses the silicon solar cell. And so now they are trying to do it commercialized, and it's already tested, is going on in some of the country in Europe and also the UK. The things are that these are fabrication is quite cheap. It's not like a silicon, and you can, when it degrades, you can reuse them. But the problem is that it's quite bit toxic, as we have a lead. So that this is the mostly challenge to get down the leakage of the lead. But the lead is bad for the human, but these are somewhere recently publication shows these are quite good for the tree. So they digest the lead, and they remove the lead from the surface of the earth. But this is not a good way. But so that's why the scientists try to do the cover with the different kind of technology to lower down the lead leakage. And you can see it very well. Now we can have it at more than 29% efficiency from the perovskite based solar cell. These are tandem perovskites, means we have a silicon and also tandem with the perovskites materials. And here the yellow only perovskite solar cell, but it is also the quite bit high, almost 26% efficiency. So, but as I told, also there is another part. As it's a semiconductor, so you can have a quantum dots you can have a quantum dots. And similar way, we can have a solution based synthesis like a colloidal synthesis. And these are the basic crystal structure we can have it from the XRD. And this, you can see this solution looks like very bright. And these are also make a, you can make a film on the PMMA, and these are quite big crystallines, and you can see they're very nice plane, and these are 5 to 6 nanometers size. And you will have a nice homogeneous dispersion and homogeneous film on the surface of your substrate, and also the TM grid. And these are the another very nice synthesis. You can show, you can see, you will have the precursor and the solvent, and you just drop, it can bright the emissions, and you will have a formation of the product, and it's super bright. So this synthesis is very easy rather than the chalcogenides controllers, like as I told earlier, lead cadmium selenides, cadmium sulfide, lead sulfides. But the problem is the stability. These are kind of ionic structure, and so stable in the normal atmosphere is not so much good. But already we have a solution, like if you have inorganic nanocrystals, you can have a very bright stable. And we need to have a coating of the like aluminum oxides and the silica coating on the surface, so you'll have a very bright emitted nanocrystals on the solutions. And you can see these are also tuned from the whole visible window emissions from 400 to the 750 nanometers. And but here it's also depends on size, and also depends on the compositions of the nanocrystals. Just you will have a different composition, like halide composition, like a chlorine and bromine. You will have a changes, because you need to have a change the band gap, because here the Bohr exciton radius is not so high, so you cannot tune the band gap size of the like a chalcogenides. But there is another possibility to get the different emissions, wavelength emission, by changing the mixture of the iodine and bromine, and and something, and this is like that. And you can have also almost NIR emissions from the iodine based controllers. If you transfer from the cesium to tin, it can have more IR. But as I told, TNR is not very stable. And also how the solar cell fabrication make, it's basically same. You have a perovskite absorber inside the P and N type electron transport layer, and these are the different kind of making solar cells. So you have a back contact, you have a front contact, and so you can have a inorganic electron transport layer, you can have a polymeric hole transport layer, or polymeric N-type layer. And from that, nowadays it's almost now people already have a 26% efficiency from the perovskites. And like these are the example, you can see it's a transparent conducting oxides, then electron transport layer, you will have a perovskites, then hole transport layer, then electrodes, and you shine lights. As these perovskites are much more stronger absorber than the quantum dots. So these are much more mostly efficient material in solar cell. And it does not so much. Also, it is applicable in the LED. There is also the light emitting diodes applications, but as I told, these are not highly stable. So LED needs the very highly stable than the solar cell material. So that's why they are not mostly interested on the LED. So people are mostly interested on the solar cells. And here you can see the electron goes through the electron transport layer, and here the hole goes through that layer, and you will have a very bright emission of the, and it's a you can have a this is the example of the perovskite solar cell. This is on glass, and also that you can have a you will have a on flexible film, because or it's a, you can make it from the quantum dots and quantum dot perovskite quantum dots, and you will have a very flexible film. So there is one video how it works in perovskite solar cells. So
Santanu,
Yes.
can you open your headphone? Then maybe we can hear the sound.
Okay, okay.
From your laptop sound,
cells consistently below the price of fossil fuels transform the energy harvesting landscape of our planet, massively reducing the anthropogenic contribution to climate change. We'd love to explore other topics in renewable energy and climate science, so please leave a comment on what topic you'd like to see next. Subscribe and click the bell icon to be notified of
Maybe I can repeat it again, so it will be more.
harvest and power our planet, with minimal environmental impact compared to fossil fuels. However, solar cells account for less than 1% of global energy production. So what's holding us back from using the technology we already have? The transition from fossil fuels to solar cells and other renewables has been a slow process over the last few decades, with non-renewables still dominating global energy generation. Until there is enough political will and renewable energy sources are consistently cheaper than fossil fuel alternatives, the world is very unlikely to make a significant enough transition to renewable energy. Since the price of energy sources varies wildly in different parts of the world, it is good to compare a metric called the levelized cost of electricity for a region, which accounts for the cost of building, operating, and eventually decommissioning a power source for every kilowatt hour of energy produced. In the UK, natural gas is the cheapest fossil fuel source and has a levelized cost of £66 per megawatt hour, whereas solar cells have a cost of £80 per megawatt hour. However, in the US, these costs are $36 per megawatt hour and $32 per megawatt hour, respectively, which is very promising. The vast majority of solar cells used today are crystalline silicon. These are what we're used to seeing on rooftops and in solar farms. The price of crystalline silicon solar cells has dropped rapidly since their inception in 1977 and is already becoming competitive with non-renewable energy sources as strong research and engineering efforts continue to drive down prices. Although, while silicon solar cells are making great strides forward, they are not without their shortfalls. But before discussing these, we have to quickly explain some basic solar cell physics. Solar cells are made from a class of materials called semiconductors. In a semiconductor, the electrons sit within a region called the valence band. When particles of light called photons enter the solar cell, some of these electrons can use this energy to jump up to a region called the conduction band. The gap between these two regions is called the band gap and is very important for the solar cell's efficiency. Once an electron is in the conduction band, it is free to move and do work on a circuit, providing energy. Silicon solar cells can achieve power conversion efficiencies of up to 26.7% for a single crystal cell, relatively close to the theoretical maximum of 29.3%. However, this high efficiency could drop off rapidly with small defects or blemishes in the material. Therefore, they have to be processed at extremely high temperatures, which makes them very expensive and time-consuming to manufacture. In fact, it is estimated that it would take around 170 years to produce enough silicon solar cells to generate the energy required to power the Earth. Another key problem with silicon solar cells is that they are an indirect bandgap material, meaning that each time the material absorbs a photon, it also requires a very specific kick in vibrational energy called a phonon at the same time to absorb this photon. This is quite an unlikely event at the atomic level, so the silicon solar cells must be made very thick to increase the chances of absorption, which massively increases the overall cost. An alternative to inorganic silicon are organic solar cells, which are made from molecules containing different combinations of primarily carbon, hydrogen, oxygen, and nitrogen. Organic solar cells can be made from liquids in a similar process to dye coating or inkjet printing. Materials like this are known as being solution processable and can be manufactured at very high throughput and at very little cost, and even on top of flexible materials. Further, because of the different combination of molecules we can choose from, we can modify the band gap, which is very important for achieving higher efficiencies. Unfortunately, organic solar cells in their current development are inefficient and often quite unstable, decomposing over time under heat, excessive moisture, or exposure to UV light. However, there is a new technology with the potential to combine the best two qualities of inorganic silicon and organic solar cells, known as perovskite solar cells. Perovskite solar cells have achieved remarkable growth since their inception a decade ago, sharply increasing in efficiency from 3.8% to 25.2%. These are made from a crystal of the form ABX3, where A is any single positively charged inorganic atom or organic molecule, such as cesium, methylammonium, or formamidinium. B is a metal with a 2+ charge, such as lead, tin, or germanium, and X is a halide ion, that is an atom such as iodine, bromine, or chlorine, with a single negative charge. Generally speaking, successful perovskite cells are a combination of an organic A site and inorganic B and X sites, combining the best of both worlds when it comes to their material properties. Perovskites, like organic solar cells, are solution processable and also very defect tolerant, so they can be manufactured at very low temperatures very quickly and can also be printed on flexible materials. The two inorganic components of perovskites give it an edge over organic solar cells in development, as they allow the material to achieve very high efficiencies. Unlike silicon solar cells, perovskites have a direct bandgap behavior, which doesn't require a phonon, and other useful physical properties allowing solar absorber layers to be very thin. Due to the different combinations available, these solar cells can also have an array of different bandgaps. This means they can be used in what is called a tandem solar cell, in which different solar cells of different bandgaps are stacked on top of each other. The bigger bandgap material sits on top, catching the high energy light efficiently, and allows the lower energy light to pass through to the lower bandgap material. Silicon perovskite tandems have already achieved 29.1% efficiency, but are still a developing technology, and will likely continue towards a theoretical maximum of around 38% efficiency. The combination of all these properties allow for perovskite solar cells to be a very cheap, high-performance solar cell, which could very well drive the paradigm shift from fossil fuels to solar cells in the near future. Of course, we are yet to see perovskites dominating the solar market, with cells on our roofs and in solar farms. So why is this? Ultimately, perovskite solar cells are just too new a technology to be seen in commercial applications yet. The vast majority of exciting results throughout this video, and in the field in general, have been conducted in well-controlled lab experiments with very small solar cells the size of a postage stamp. The first main challenge here is to be able to scale up these cells to be large enough for solar panels, which poses both a very significant engineering and scientific task. The second main challenge is to be able to have these solar cells last for a long time. Silicon solar cells already last reliably on rooftops for around 30 years. Developing perovskites that can avoid being broken down by moisture, oxygen, and UV light is another significant task needed before perovskites will challenge silicon and ultimately fossil fuels. A third important challenge is to replace toxic lead from the system, as it could be damaging to health. This could be replaced by other similar metals such as tin, but is also a relatively new research area. Perovskites are likely to play a significant role in the near future of renewable energy generation and will hopefully be a key component in bringing down the price of solar cells consistently below the price of fossil fuels, transforming the energy harvesting landscape of our planet, massively reducing the anthropogenic contribution to climate change. We'd love to explore other topics in renewable energy and climate science, so please leave a comment on what topic you'd like to see.
So, these are the other applications, also the perovskites, like it's a perovskite printing, and this is also the LED display, but these are not comparable with the quantum dots till now. Also, there are some lasing related applications, as it is a very bright emitting material. So it's like this. And finally, thank you to all of you to attend this talk.